so as promised, we have a video about sort of the conceptual aspects of Chapter 5. As we talk about gases, we've been doing a lot of math and making a lot of equations, and now we're going to take a minute about sort of the theory behind it all. So we know we know about gases. We have a sense, right, of how gases behave, maybe because we've just talked about it in this class or just from your real-world experiences. These are some macroscopic, right, large-scale things we can say about gases. So macroscopic. So we know that gases completely fill their container. We know that they take the shape of their container. We know that they have relatively low densities because there's less mass, right? If density is equal to mass over volume, there is less mass in a given volume, and so the density number goes down. When this numerator is little and the volume is big, we have, circles. Guys. Okay, so when that happens, we know that the density can be a pretty small number, right? We know that they are compressible. In fact, they are the only compressible phase that we know. Liquids and solids are not. And we know that these guys always make a homogeneous fluid, but we've called these things homogeneous solutions, right? We talked about solutions in Chapter 4, but we can also call them just mixtures, right? So mixtures were a category of the classification of matter. So we know that all of these things are true, and they're true on the macroscopic scale, so we can see them, right? Macroscopic means that it's something that can be observed. So these are observable characteristics, right? Now, there is a theory that explains why those macroscopic things are true, and we call that the kinetic molecular theory. The kinetic molecular theory is really just describing the microscopic behavior of the molecules. So this is the stuff that we can't see, but these are the microscopic things that have to be going on in a gas to make the macroscopic things true, right? So the theory is just describing what the tiny particles are up to. And so it says over here that the molecular theory is the simplest model for the behavior of the gas, and that we're going to treat this theory as a collection of particles, right? So it's the microscopic understanding that creates the macroscopic world that we observe. So chemists do this all the time, right? We make theories about stuff that we're observing. So there are a couple of things, maybe 5 or 6 things that you have to know about the kinetic molecular theory. They are pretty obvious. They're not particularly tricky, but you have to know them because it's going to come up in multiple choice questions on the exam. It's also going to come up in short answer questions. So the first thing that we have to know about the kinetic molecular theory is that all particles of gas are in constant motion, right? They're always moving around, zooming around space, either in a balloon or a cylinder, wherever the gas particles are. They're always moving. They never rest. That's the first thing you have to know, that we assume to be true about gas particles. The second thing you have to know is that we assume that the attraction between particles is negligible, and in fact we assume that it's zero. So if this gas particle, I was just about to draw a circle, oh my gosh. Okay, let's say he's a square. So that guy's a square. When they are moving beyond one another, so they're just shooting around in random directions, right, around space, they do not know that the other guy is there. They feel no attraction. That's important, right, because of the way that we've modeled the system mathematically, and we'll come back to that in a couple of slides. Okay, so the next thing that we believe to be true about the way these particles behave is that when a moving gas particle hits another one or hits the side of the container, they're not sticky. They have no moment where their attraction is measurable. So it means that they bounce off of each other perfectly elastically. So this is where we say that we believe that they are elastic collisions, meaning they conserve They conserve their energy, right? So if this guy, circle, happens to bounce off of this guy, they come together, they hit. It's a perfectly elastic collision. There's no moment where they pause to hang out together, and then they immediately bounce off one another, completely elastic. No attraction, no stickiness. This is also going to come back and become a problem when we think about the ideal gas law. So we're going to bring all of these tenets of the kinetic molecular theory all together in an equation in the end. Okay, the other thing that we assume is that there's a lot of empty space between the gas particles compared to the size of the particle. So really what we assume is that the volume of the gas particle themselves is unimportant. So we assume the volume of the gas particle. Could be a molecule, could be an atom, right? Is 0. We assume it takes up no space. So in the kinetic molecular theory, when we describe a gas, we know it's not true, but to make the math simple, right, all the math that we did this chapter is highly simplified. This is a little piston, right? A hand could come, look at this hand, it's amazing, that's a hand attached to an arm. Yep, and he could push this down. This is a brilliant picture. He could push that down, and if he did, right, even if there is a gas in here, we would assume that at the end, when he was done pushing it down, the piston would sit right, so close. The piston would sit right down here, that there is no volume. If we press all the way down on the gas, there's no volume taking up space because of the particles. So there's my hand. Okay, right? So there is no volume due to the gas. We're going to get to another slide where we talk about why that's problematic in the way that we've set up our equation, right? This equation assumes that all of these things are true. So all the math that we've been doing is based on all of these assumptions, right? We could call these assumptions. We sort of know that they're cheating, right? We're sort of cheating here by making these simplifying assumptions, but it's the way to make the math doable, right? So we're going to talk about those when we get to the end of the slides. Okay, the other two things that we have to understand about the way the gases are moving around is that the average kinetic energy, right, or the average speed, I mean, kinetic energy is really just motion. So the average speed of the gas particles are proportional to the temperature in Kelvin. So the hotter it gets, right, temperature goes up, the faster the molecules move. Now, not all gas particles are moving at the same speed, right? So I likened this in class, although I don't know if everybody was listening when I was talking about it, but if someone pushes, say, me, right? Oops, here's Dr. Fuller. Hi. And then maybe like a little kid, right? Don't push little kids, that's messed up, but you know, let's say there's a little kid. Little kids have hair. Okay, so if you were to push me with the same amount of energy you pushed a little kid, he's going to go a lot further and he's going to go a lot faster because he has a smaller mass, right? So things with heavier masses can receive the same amount of energy, right, kinetic energy, as something with a heavier mass, and their speeds are not going to be the same. So the kinetic energy of the particles in a gas system, those are the same, right? We've given them the same energy. Their velocity, not the same. They're different, right? Lighter things go faster, right? So we're going to come back around and talk about that in a little bit as well. Okay, and then this is kind of the last point here is a reiteration of the one that we made before, which is that the collision of one particle to another is completely elastic because we assume there is no attraction, right? The reason why these are elastic is because we know it's not true, but we choose to ignore the attraction between the particles. Because it makes our math simpler. Right? So those two slides I just went over, this slide and the last one, are all of the things that you're going to be responsible for knowing about the kinetic molecular theory. You have to understand that we think that the volume of the gases is negligible. You've got to understand that we think that their collisions are elastic. You have to understand all the things that were pointed out on these two slides. Okay? So we're going to skip this slide. These slides are posted on Blackboard, and when you go through them yourself, when you download them and study them for the exam, you can just skip past that guy. Okay, it's true. All of those things on that slide are true, but we already talked about those on the first day of lecture, so I don't want to reiterate them here. Okay, so here's the mathematical proof that the temperature and the molecular velocities are proportional. This tells us that the kinetic energy of a particle is equal to some values, right? Some constants, the mass and the velocity, right? So this is the mass and this is the velocity. So they're equal to each other, but as the mass goes up, right, the velocity goes down. So heavier things move slower. That's really all you need to know about the relative speeds of gases. Heavier, slower, which makes total intuitive sense, right? So down here, the mathematical description tells us that the relationship between, this is the velocity, so the speed, is indirectly related to the mass. This is the molar mass of the gas. So as the molar mass gets bigger, the denominator gets bigger. As the denominator gets bigger, the value of this fraction gets smaller, right? So however you need to mathematically prove that to yourself, you can either use this mathematical expression or this one. You won't have to crunch any numbers on the exam or even on the final. We're not going to make you calculate this, but you need to understand the relative relationship, right? So the heavier they are, the slower they go. Remember, though, the kinetic energy of all of the particles is the same if they're at the same temperature. So the kinetic energy of particles are the same at the same temperature. And so in a beaker, right, all of the gases are exposed to the same temperature. But maybe we have some, oh, that was a nice circle. It didn't freak out then. Okay, so we have little gases and we have big gases, right? And so maybe this guy's like really heavy. Maybe he's got like a really heavy molar mass like CO2. And maybe this guy's got like a little molar mass like H2. They're all at, let's say, 30 degrees C. They all have the same kinetic energy. And they all are experiencing the same amount of kinetic energy put into the system, but some of them have faster velocities, right? So this guy has a low velocity, and this guy's going to have a really high velocity, right? Because he's experiencing the same amount of energy, but what they do with it is different. So this guy will have a high velocity. That's what you have to understand, right? So here's that in a picture. So these are the relative number of molecules with the indicated velocity. So the higher it is on the scale, oh boy, the higher it is on the scale, the more atoms feel this way, right? This is just the total number of particles. This is the molecular velocity, and this is at some temperature. Let's say that this graph is showing us a temperature of, I don't know, let's say 295 Kelvin. Right? All of these particles are at 295 Kelvin, and when we look in here, we can see that the heaviest gas among them, this guy weighs 32, this guy weighs 28, this guy weighs 18, this guy weighs 4, and this guy weighs 2. We can see that the heavier they are, the slower they're going. So if I look down here, right, this guy's moving at just under 500 meters per second. Right, there are my units. But H2, while his average is spread out, the average speed for H2 is somewhere over here between 1,500 and 2,000 meters per second. The lighter guy moves faster. Right? So you've seen it in equations, you've seen it in words, and now you've seen it in a picture. So you know this is going to be something that's going to come up on the exam. So make sure you understand that. If you don't, you can always shoot me an email. Okay, so real gases. We have learned about the ideal gas law, right? We learned about something called the ideal gas law. It's ideal because we ignore all the things that make it problematic. So we ignore attractive forces, we ignore the volume, right? We made all of those assumptions in the kinetic molecular theory. We assumed a lot of stuff to make an ideal system, right? We ignored all of the annoying things. We ignored attractive forces. and we ignored the volume of the particles. We said, oh, it's too hard to worry about, we'll call them zero. We know that the volume of a molecule is not zero, but we said that the volume was zero. We ignored all of the tricky things. Okay, so as it turns out, ignoring all of those things means that we've solved the ideal gas law, and it doesn't really apply to real gases. So that's the secret's out. So real gases often do not behave like ideal gases. At high pressure, that's particularly true, or low temperature. So when we're really high pressure or really low temperature, all of these things that we ignored, they come back to haunt us, okay? So these things are fine. All of these assumptions are fine for us as long as we're at normal pressure and normal temperature. They become really problematic when we are at high pressure, so lots of pressure on the system, or really, really low temperature or low energy. Okay, so because the ideal gas law assumes no attraction and assumes the particles don't take up space, because the kinetic molecular theory told us we could do that, right? It's based on these two things. We were fine to look at these equations in class, this PV equals nRT. But as soon as we break these pressure-temperature rules and we look at high pressure and low temperature, the ideal gas law sort of begins to let us down. Okay. So at low temperatures and high pressures, the assumptions that we've made are not valid. So we're not going to look at this particular graph right here. You don't necessarily have to understand it. You can look at it if you want, but it's not going to come back on the exam. And then let's do that. So let's talk about this. So real gas behavior. We said, and I drew my little hand, right, up in the earlier graph, we drew my little hand and he was pressing down on the piston. And I said if it was an ideal gas, if we were following the kinetic molecular theory, this guy could make it all the way down to the floor and the volumes of these green guys wouldn't matter. But that's not true, right? Real molecules do take up space. So our simplifying assumption to ignore volume, that's no good when the pressure is really high, right? When the pressure is really high, it matters that these guys are actually taking up space. So that's a deviation, right? And so this non-ideal behavior, the place where the ideal gas law fails, is that there is a particle volume that we have to take into account. So good news, this guy van der Waals, who you'll learn more about in Chem 104, came up with this. So this is PV equals nRT, right? But it's just solved for the volume, right? So they divided away the P, and now we have the volume is equal to nRT over P. So that should be cool. We know where that came from. But it turns out this is true for ideal gases, but it is not true for real gases. Real gases, our volumes would always be, the real gas volume is always bigger, right? Because over here we said that the volume of the particle doesn't matter. And over here we're suggesting that it does, right? We can't say that there's no volume to a molecule. So because every little molecule really has volume, we have to add in a corrective factor. So B, the van der Waals constant, it's different for every molecule because molecules are different sizes, but this is where we add in a correction factor, right? So that's a little correction factor to the ideal gas law. Correction to the gas law. So NB. Now we're not going to talk about what NB means. N is moles. B is the variable. But you have to know that it exists. You have to know that there's a corrective factor that has to be applied because in real gases, the molecule volume is mathematically important. So there's that corrective factor. The other thing that we assumed is that when two molecules collide, they don't get stuck, right? We said there was no intermolecular attractions. We said there was no stickiness, right? But that's actually not true at really low temperatures, right? At really low temperatures, these molecules barely have any average velocity. So this guy's kind of moving really slowly towards this guy, and if it's really cold, he's moving really slowly. And so when they really hit, they hang out for a minute because it's really cold, right? And when it's really cold, everything just moves really slowly. And so at low temperatures, they are a little sticky. There are attractive forces that matter, right? At low temps, attractive forces matter. And that's actually going to affect the pressure inside of the ideal gas law. So just like we had to come up with a corrective factor for the volume, we also have to come up with a corrective factor for the pressure. Because at low temperatures, these low-G molecules kind of lumber into each other and they end up getting stuck. So van der Waals came up with another corrective factor. He called this one A. A adjusts the pressure, right? A has to correct the pressure that is in the ideal gas law, and it's a decrease. When these particles get stuck together, it actually decreases the pressure from the ideal behavior. So this is the ideal pressure, and this is a decrease in the ideal pressure when we look at the real pressures. So these are the real gas law pressures, and we're decreasing, it decreases from the ideal. So the ideal gas law underappreciated the volume and overappreciates the pressure, and so we had to come up with another fairly complicated corrective factor. So if you put all of these together, you actually get the real gas law, not the ideal gas law. And so here it is, right? When you're looking at ideal gas laws, we just said, okay, it's no big deal. It's PV equals nRT. And the only reason we can do this is because we followed the kinetic molecular theory model. So we're okay to solve this here in freshman level chemistry. But if you're a gas chemist, if you're going into like materials engineering where you're going to evolve gases from some of your polymers or whatever you might be working on, you're going to have to add in these corrective factors, right? So one of them corrects the volume and one corrects the pressure. You will not have to do this math on the test, so no math like this on the test. But I have to make you aware that these corrective factors exist. I can't let you just go on only living in PV equals nRT. I mean, that's what we did mathematically for now in this class, but that's just some high school stuff, right? That's not the full picture. So when you go on to higher level college courses, you're going to need to use this formula that is applicable to real gases without using the simplifying assumptions of the kinetic molecular theory. So that's what this whole lecture has been about, is this slow lead up to how the equation that we've just been dealing with for the last week and a half is actually a highly idealized, unrepresentative example of algebra being applied to a chemical system. So if we want to look really quickly at how ideal gases really are, this pink line solves the ideal gas law in this weird way. So these axes are pretty hard to understand, but we can just see visually an ideal gas across multiple pressures should behave like this, right? This is what ideal gases need to look like. But you could see that some gases are underestimated across some pressures, and then some gases are way overestimated. The important thing to see, though, is no gas really behaves like an ideal gas, right? This ideal gas equation, this PV equals nRT, does a pretty bad job at estimating pressures, volumes, and temperatures of real gases, right? So this math was really easy for us, and so that was good, and we all learned some things about units and pressure, but as you move on to higher level courses, right, we're going to have to move away from these highly idealized formulas because they actually do not predict the behavior of real gases. So you're going to be responsible for these ideas, both what is in the kinetic molecular theory and then how all of the ways in which the kinetic molecular theory and the ideal gas law are incorrect. So you've got to know both parts of this for the exam. There are questions on there about both of those. You can read more about this in your textbook. You can come to the review session on Sunday night from 4 p.m. to 6 p.m. in Hayward 201, or you can send me an email if you have any questions about this. Okay, that's your video. Good luck studying for your exam.